Hello everyone, welcome back to the channel. In today's lecture, we are going to solve the Legendre differential equation using the power series method. So we will derive the recurrence relation step by step and see how the power series solution leads to the Legendre polynomials. So without further delay, let us get started with the derivation. Now in today's derivation, when we are considering this Legendre differential equation by power series method, we are solving it. So we need to consider the Legendre differential equation, right? So Legendre differential equation is one minus x square d square y by dx square minus 2x dy by dx plus n into n plus 1 into y is equal to 0. People also write this as 1 minus x square y double dash minus 2x y dash plus lambda into y is equal to 0, where lambda is equal to n into n plus 1. Alright, so let us consider this equation as equation 1. Now if we are considering the Legendre differential equation and we are solving it to get the solution of this Legendre differential equation. Now as I said, the Legendre differential equation is not solved, or it is not solved by the elementary function. So hence we are going to use the special functions as a solution to this Legendre differential equation. So here we are going to assume a solution, right? So what we are going to do, we are going to assume a solution to this equation, and then we are going to check whether that assumed solution is satisfied by this equation 1 or no. If it is satisfying, then we say that the assumed solution is a solution to the Legendre differential equation. So let us consider a solution to equation 1. Okay, as now y of x is equal to series of solution we are going to consider. So summation n is equal to 0 to infinity an x raised to k plus n, right, where first term we are putting the condition that it is not equal to 0. People also consider this power series method and the Frobenius method, right, to solve such differential equation. Now Frobenius method are closely related with this power series method, but they are not exactly the same. So Frobenius method is a more general method used when the point of expansion is regular singular point, right? So when it is regular singular point, we consider that as a Frobenius method. Okay, sorry, we consider it as Frobenius method. However, for the Legendre differential equation, we are expanding the solution, and which is a ordinary point. So the ordinary power series method is sufficient, and there is no need to use the more general Frobenius method. So with that understandings, let us continue with the power series method. Now, since we are considering y of x here as a solution to the Legendre differential equation, since I have y double dash and y dash in the differential equation, I need to differentiate this y of x. So I'll differentiate the equation with respect to x to find y dash of x. Now, y dash of x is nothing but summation n is equal to 0 to infinity constant into function. All right, so an k plus n into x raised to k plus n minus 1. Right, so let us consider this equation as 2 and this one as 3. Right, and also let us find y double dash also. So y double dash, I'm going to differentiate y of x equation 2 twice to get y double dash of x. So summation n is equal to 0 to infinity. Now again constant into function. All right, so it is an into k plus n into k plus n minus 1 into x raised to k plus n minus 2. Now let us consider this equation as equation 4. Now since I have got y of x, y double dash of x, y dash of x, so let us substitute back into this Legendre differential equation, that is equation 1, to check whether this equation satisfies or no. So let us substitute it. Now it is 1 minus x square. Legendre differential equation is 1 minus x square. So before going to that, let me write here as substitute. So this is the process that is followed in power series method whenever we are finding a solution to the Legendre differential equation. All right, so substitute equation 2, 3 and 4. All right, substitute equation 2, 3 and 4 in 1. Now we are going to get it as 1 minus x square, and y double dash is summation n is equal to 0 to infinity an k plus n into k plus n minus 1 into x raised to k plus n minus 2. Right, okay, minus, so let me take that 2x into y dash of x, that is summation n is equal to 0 to infinity an k plus n x raised to k plus n plus lambda into summation n is equal to 0 to infinity an x raised to k plus n is equal to 0. So let us simplify this. So multiply terms with the bracket terms here, right? So we are going to study it as an. So let me take summation n is equal to 0 to infinity an k plus n into k plus n minus 1 into x raised to k plus n minus 2 minus, right, minus x square term, right? So it is summation n is equal to 0 to infinity an k plus n into k plus n minus 1 into x raised to, here plus 2 and minus 2 will get cancelled, so the power of x would be x raised to k plus n. Alright, so minus 2 into, multiply this x term with this bracket term, it would be 2 into summation n is equal to 0 to infinity an k plus n into x raised to k plus n. Alright, plus lambda into summation n is equal to 0 to infinity an x raised to k plus n is equal to 0. So since we got this terms, now just look at this. You have a power of x as x raised to k plus n minus 2. You have x raised to k plus n, and here x raised to k plus n, x raised to k plus n. So group them all and simplify it. So just group the powers of x, common powers of the x, into 1. So it would be, so let me take summation n is equal to 0 to infinity an k plus n into k plus n minus 1 x raised to k plus n minus 2 minus, so all these things, this, and this, right? So group all those three into 1. It would be minus summation n is equal to 0 to infinity an is common in all the three, so take out the common thing, an into k plus n, k plus n minus 1, yes, plus 2 times k plus n minus lambda, right? So the whole thing with the power k plus n, that is equal to 0, right? So let me consider this as my equation 5. Whether that is 5? Yes, it is 5. Now if this is my equation which has given me the coefficients with power x raised to k plus n minus 2 and with the x raised to k plus n, right? So here if I am equating the coefficients of like powers of the x to 0, so what do I get here, right? So let me consider it. equating the coefficients of like powers of x to 0, right? Because that would give me a indicial equation. All right, so you'll get to know what is that indicial equation is. So when n becomes 0, right, I can get the lowest power of x, the lowest power of x, right? Now just see, you had x raised to k plus n minus 2 and another power was k plus n. So if I substitute value of n as 0, I would get the power as x raised to k minus 2 and another with x raised to k. Now if this also becomes 0, now the lowest power would be this. Now coefficient attached to this power, if I equate this to 0, since the RHS is also 0, I can equate the coefficient here to 0. Now if I'm equating this equation, what we call it as the indicial equation. So we are going to calculate that indicial equation here, right? So let us calculate that now. Now it is nothing but the coefficient is, just check what is that coefficient is. Now it is nothing but this one, right? It is, so it is a, if I am taking n as 0, it is n a naught into k, sorry, k into k minus 1. This is becoming 0 since the RHS is also 0. So we are considering that equation. So it is nothing but a naught into k minus 1. So this is equal to 0. Now this is nothing but my indicial equation. Now since we had put the condition that this a naught is not equal to 0, nothing but it is an arbitrary value, right? So this cannot be 0, so obviously this can be 0 here. So I can take k into k minus 1 as 0, which implies k is equal to 0 or k equal to 1. Now next power of x would be what? Now the next power of x is when n is equal to 1, right? So let me calculate that next power of x, right? So why we are calculating all this? Because we had considered solution as y of x as series of terms containing n is equal to 0 to infinity a n x raised to k plus n. So we had put the condition here that a naught is not equal to 0. So we are checking if this is the assumed solution, then this has to satisfy the Legendre differential equation. Now we are checking all those values under this summation. Now the first value is when n is equal to 0, right? So if n is becoming 0, I am finding the value as n naught x raised to k plus 0. That is what, nothing but this term, right? Now if I want to calculate the other power of x, nothing but with this increase in the power of x, I need to go for the second value, right? So that we are going to check. So if n is becoming 1, for the next power of x, obviously it is k plus 1. So n is becoming 1 here. So we are considering that, right? Okay, fine. So for the next power of x, when n becomes 1, your initial equation would be a1 into, just substitute the value of uh, n here. Okay, so it is k plus 1 into k is equal to 0. Now since I have the values as k is equal to 0 and k is equal to 1, use those values now, right? So for k is equal to 0, I have a1 as, just check, put the value of k as 0. You'll get what? a1 will be a arbitrary value, right? Now for k is equal to 1, a1 will become 0. So a1 is becoming 0 for all the values of k. So to get the coefficients, I need to check for all those. N is equal to 3, n is equal to 4, 5, 6, everything up till infinity. So in order to consider all those infinite value, I need to check for all those infinite values of a, right? So practically it is not so possible, right? So what we are going to do, we are going to generalize the equation here. So that generalization we are going to do it now, just by considering the next coefficients as the value of n increases. Now how that value of n is increasing, that we are going to do it now. So let us check that. Now if I am going to check for the next coefficient, right? So the coefficients of x, what I'll do, I'll make one adjustment here. Now what is that adjustment? What I'm going to do is, I'll just substitute the value of n as some j plus 2. Why I'm going to substitute that j plus 2? Now just go back to the equation here. Now you have this equation 5, right? So here just check. This is with a power x raised to k plus n minus 2, and this is with x raised to k plus n, right? Now in order to make this power as equal, in the sense, in order to make the two terms as one, I'll take the power as same. So what I'll do, I'll take value of n as j plus 2 in this first summation. Now if I'm taking j plus 2 as first summation, what it will do, I'll get the power as k plus j. In the second summation, what I'll do, I'll make an adjustment of choosing the n value as j. If I take n value as j, this will become k plus j. If I take n value as j plus 2, I'll get the first term with a power k plus j. So I'll make these two powers as equal power just by taking the value of n, right? So I'll take n is equal to j plus 2 in first summation and n is equal to j in second summation. Now if I am making these corrections, and then what I'll do, I'll equate it to 0. Then equate it to 0. Now if I am equating it, what will be my coefficient now? The revised coefficient would be a j plus 2. Why j plus 2? Because the first summation is having the n value as j plus 2. So k plus j plus 2 into k plus j plus 1, right? I'll take that minus term to the other side. It would be aj because the second term is containing n value as j. So k plus j into k plus j minus 1 plus 2 times k plus j minus lambda. Right? Now what I'll do, I'll put those conditions. K is equal to 0 because k is equal to 0 is what? In which a1 is becoming arbitrary value. Yes, that a1 term exists. Okay, so now what I'll do, I'll take that. Now just simplify these. Can I write this equation as k is equal on taking k is equal to 0 into consideration? I can write this equation as aj plus 2 as j square plus j minus l square minus l divided by j plus 2 into j plus 1 into aj, where lambda I can take it as n into n plus 1. To be particular, this is nothing but the quantum number L into L plus 1. Alright. Okay, in physics we are going to use that. Yeah. So on rewriting, what I can get is, on rewriting, I'll get aj plus 2 as minus L minus j of j plus L plus 1 whole divided by j plus 2 j plus 1 into aj. Now let us consider this as equation 6, and this equation we are going to call it as the recursion relation. So this is my recursion relation. Now why we are calling this as recursion relation? Because this relation gives me all those coefficients if I am changing the value of j. Now if I just substitute the value of j as 0, I may get the next coefficient, that is a0. So whatever I'm having as a series of terms from n is equal to j to infinity, an terms along with x raised to k plus n. So here k is becoming 0. So obviously I'm getting an x raised to n. So as I go on increasing the value of n, if I'm substituting the value of n as 0, 1, 2, 3 and all, I may going to get all these coefficients which are the coefficients to this power of x. So that coefficients we are going to generalize this using this recursion relation, and that is obtained whenever I'm going to change this value of j, right? So this relation is called the recursion relation, which gives me all those coefficients, right? So just by substituting the values of j, we are going to get all those coefficients. So in the next session we are going to get the different coefficients which are possible for this uh, solution. So the second part will be continued in the next video. I hope you have understood this, and thanks for watching, and wait for the next. Thank you.